right, good afternoon and welcome. Let's begin. First things first, anybody else want to turn in their homework? Any other papers? I noticed a couple of them weren't stapled, and that's just a recipe for disaster. Your work is likely to be scattered across the earth if you don't staple it all together. So please be sure to do that before coming to class. I'll do it this one time just because I'm such a nice, generous guy, but in the future, please handle that yourself. Let's look a little bit into the announcements here. Friday, we're going to have our first quiz of the semester, and that's covering the first 7 lectures, inclusive of today's material, and the concepts that you did in homework 2 and 3. Now, this isn't anything to get too worked up about because it's just 2% of your course grade. It's really more of an opportunity for you to check for yourself whether your study methods are working, whether when you solve the problems, if you actually know the material. So we're going to have that at the beginning of class, and you'll definitely want to arrive on time that day because you'll need as much of the time as you'll have available. Also, bring your computer to class on Friday because we're going to get our first taste of using Excel to solve these problems. And so if you have a laptop available, it'd be great for you to bring one. It's not mandatory, of course, but it'd be very helpful. And then the next homework assignment that I've given you today, hopefully everyone got a copy of that. Now, it looks worse than it is. It looks like this is, wow, such a long assignment. It's not actually that long. It's just that I've given you a lot of hints on how to solve the problems. And so it's only 14 problems. I guess 14 makes it sound big again. It's 14 problems that I've given you a lot of hints on. So that'll be due Monday. All right. So any questions related to these announcements or what we've got going on? Yeah, the homework that I'm turning back is there. I put it into a couple of piles so you can pick that up afterwards, yeah. Other questions? Okay, we've got a lot to cover today. We're going to be talking about kind of the easy way to solve these time value of money problems. And one of the handouts that I had back here today was this interest factors. Anybody need that? Interest factors. Everybody have this one? Okay, I put the holes in it so you can add it to the binder you're collecting for the course. This is some really important formulas that you can use to solve these types of problems, to find the future value when you're given a present amount, to find the present value of a future amount, and so on. You'll notice that there's a standardized symbology for summarizing what this problem is going to be, solving for. So the F/P we've done before. We've talked about how that means to find one thing given another. Now the I here, what you'd normally do when you're summarizing a problem statement is, first of all, you'd say what kind of a problem it is. So it's maybe an A/F problem, an F/A problem. The next thing is you'd actually find in the problem statement where it says what the interest rate is. So you'd say I equals 8%. You just put that inside of the brackets. And then N is referring to the number of years. And so if you're moving some future value amount from year 10 to year 0, then N equals 10. So it's a pretty self-explanatory and compact way to summarize these problems. With the formula column, you can see how you'd be able to calculate the factor for any interest rate and any N value. In the back of your book, these have been calculated for a variety of different interest rates and N values, but not for every interest rate. For example, it has 2% interest, 3% interest, 4%. I think it doesn't have 3.5% interest, or it doesn't have 17% interest. It may have 16 and 18, but it sort of jumps around. And it also, as far as the N values go, when those tables are provided, the N values go from 1 to 50, and then I think it goes 75, 100, and so there may be N values that a pre-existing table isn't available for you. In those cases, or when the problem statement says to use the equation method, then you can substitute into the formula itself, and you'll come up with the ratio that you would need to solve the problem. And so, for instance, capital recovery, that's where you're going to find an annual value given some present amount. You'd solve for that factor, and then you'd multiply it by the present value in order to find A. So we'll get our first taste of calculating these factors and using them today in class. Here's what those tables look like. You'll notice that n value is each row, and then here's the p, f/p. And so what that means is you're going to find a future amount based on a present value. And you'll notice that these factors are increasing above 1. But the present value, based on some future amount, the factor is going lower and lower as you have the n value increase. Why is this factor getting lower? What's the interpretation of that for the present worth column? Okay, you're right. So you have some future amount. Let's say that for row 8, you've got some money in year 8 years in the future, and you want to find out how much is it worth today. Remember, money today is more valuable than money in the future. So some amount in the future isn't as valuable today as the money that's already in today, and so it has to be discounted. And that's why these are less than 1, why we call it discounting, moving money from the future to the present. And likewise, these values being larger than 1 applies when we're compounding, which is moving money from the future, from the present into the future. All right, so let's just look at some examples. These aren't necessarily anything that you have to do the calculations on. You can if you'd like. We're not going to stop talking, and this isn't an in-class exercise quite yet. I just want to illustrate how we use the factors and how we translate the problem statement into what we need to solve it. So a person deposits $5,000 into an account. So that means that's happening today. That's a present value. Interest rate of 8%, so I equals 8% or 0.08. And then the amount in the account after 10 years is closest to, okay, that's defining n equals 10. Okay, so putting money into the bank, and it's going to be compounding over time. Even if you're just guessing, you can eliminate answer A, because the balance in the account isn't going to get smaller over time. The interest amount is going to be larger. So we need to find which of those 3 it is. So the cash flow diagram is always a great place to start when you're doing a problem like this. And this is, we're depositing some amount, $5,000. Over 10 years, nothing is happening until we withdraw the amount at year 10. And so we're trying to find out what is the future value. So that's what the cash flow diagram summary of the problem looks like. So here's the factor summary of the problem. We have a present value that's defined, and we want to know the future value. So we're going to multiply that by the ratio of future divided by present. So this ratio, f/p, will allow us to find future given present. 8% table is where we'd go to look it up, and 10. So if I go back to the previous slide, which is the 8% table, let's find for row 10 the f/p column. Okay, so here's the 8% table, f/p, row 8, so 1.8509. Oh wait, did I look on the wrong thing? f/p. f/p. f/p, 8%. Oh, 10, right? n equals 10. I was looking in row 8. 8% is the interest rate. It's not the number of years. Okay. So 10 years, 2.1589. So we'd take that factor, which is the ratio of the future amount to the present amount. So the account value is going to go up by 215%, in other words. So we multiply that ratio by the amount, and we get the value of the account. So answer C of those options is there, 10,795. So any questions on the solution strategy of first making a cash flow diagram, then trying to understand what's the given, what's the unknown, finding the factor, look up for it. Any questions about the process? Okay, well, let's try it with this one. Company wants to make a single deposit now, so we'll have enough money to purchase a backhoe costing $50,000 5 years from now. Okay, so this is going to be $50,000 in the future. And we already have n equals 5, so the future value is known, the present value isn't known. The amount that must be deposited now. So that's the unknown. And if we summarize that as a cash flow diagram, you'll see that we're going to do a withdrawal in 5 years of $50,000. The present value we have to put in the bank to make that possible in the future is what we don't know, and we're making 10% interest. So with this interest factor handout that I gave you, what you could do is you could calculate the factor that is needed. See, this is 10%. So I can't go to that table I was using before on the previous slide because that was just the 8% table. So 10% is going to have a whole different set of factors on that page. So one way to do it would be to find out, all right, so if this is find P given F, that means we're looking for the P slash F. So single payment present worth converts to P given F. So that's the one we have, the second row in the handout. Well, the formula is just 1 plus I to the negative n power. So it's going to be 1.1 to the negative 5 power, and that would give you the factor that you have to apply in the formula. So that factor is 0.6209. Now, the tables that you can look up in the back of your book are often rounded off. They can't just put an infinite number of decimals or else they wouldn't have room for all of the different columns in there. So 0.6209 is different than what you'd maybe get if you actually put it into your calculator. So you need to be aware that sometimes there are going to be slight differences between the answer you get from just applying a looked up table factor versus solving it yourself and leaving all of that precision in the calculator based on the interest factor formulas. So just be mindful of that. So we multiply the factor by the future value, and the present deposit has to be 31,045 according to this, so we'd choose the most nearly one, which is answer B. Okay, so any questions about how you'd use these interest factors in the handout that I've provided? We've already seen annual series, but let's refresh our memory about the standard assumptions of an annual series. The first thing is that the equal amounts begin the year after the present value. And so these are consecutive payments. There can't be any interruptions. It has to be the same amount each time. So bullet point 1 and 2 here, consecutive and the same amount. So the height of each of those arrows will be the same. That means it's the same withdrawal amount every year or the same deposit amount each year. And then they occur at the end of the first year is when they start. And so in year 0 corresponds to the present time. At the end of the first year is when the deposits or withdrawals occur. And now here's how you'd summarize a problem statement like this in this kind of equation method of doing it. It's a P slash A problem, so find P given A if you actually know the amounts of the withdrawal here, and some interest rate would be given, and as pictured here, n equals 5, because there are 5 of them, 1, 2, 3, 4, 5. We can also do problems where we're trying to find the unknown A when we're given a P, and so it's going to be a different table lookup value for P slash A versus A slash P. It's easy to mix those up, so be careful that when you're looking on the table factors that are given that you get the right one. All right, so I actually would like you to solve this one. Even if you can't do the calculations, try and identify what's the given, what's the unknown. Here we have The problem statement, I won't read it to you. I'll let you read it. I'm going to bring up the lights, though, so that you can do your calculations a little more easily. So a great place to start, if you're stumped, is just with the cash flow diagram. If you can't do anything else, try and break the problem down into the cash flow diagram. I've just put the cash flow diagram on the screen there to see if it matches what you've done. Question? You can, if that's easier for you. I think it's better to write the actual amounts because, pretty soon thereafter it's going to be like partial dollars and stuff, like you wouldn't want to put 14.8137K, So the formula for this one's pretty messy, right? This is not the worst one, but it's helping you to understand why maybe these table lookup factors, when they're available, is the way to go. We're trying to find P given A, and the formula for that, if you look on the handout that I've given you, so for 10% it will be, let me do this. 1.1 to the power of 5 minus 1, and then 0.1, 1.1 to the 5. Okay, let me get out my calculator, see what we get for that. Did anybody else get 3.7908 for the factor? Okay, well, hopefully we're both right. Let's take a look here. We'll do the big reveal. Wish there was an easy way to erase all this. All right. So we use the factor of 3.7908 that we calculate from the handout, or if we're lucky from the table that's provided, multiply by the 5,000. So the present value that we have to invest now is $18,954. So the problem statement said just to break even. What that means is, if you spend more than this $18,954 to improve this process or whatever that's happening, we don't actually care what's necessarily happening. We're just mostly interested in the cash flow aspect of it. We're accountants at the moment. So you make some investment, you get some return over time. What this is saying is if you invest more than $18,954, then you'll actually be losing money on the deal. And if you invest less than that amount, then actually it will be a profitable investment. But this is the maximum amount that can be spent in order to justify what's happening in the future. So any questions on this example or how we solved it? Okay. So we looked at P versus A. Now let's take a glimpse at the standard notation for F versus A. Now this is a little bit different because, you know, the amounts are still the same and it's consecutive years, but in the previous slide when we had P, it was in year 0. Here, when you're solving for a future amount, like a lump sum future equivalent of an annual series, it happens in the same year as the last payment. And so it's kind of counterintuitive. You'll notice here that there's 1, 2, 3, 4, 5 payments, and then the single future amount is in the same year as the terminal payment, so in year 5. Now, what's strange about this is it's sort of like you're saying the bank is going to give you a loan, like every year they're going to give you a certain amount, and then you have to repay it at the end of 5 years. And so what this cash flow diagram is saying is that they give you your last payment the same year, at the same moment actually, that you have to turn right around and pay them back that amount. It's odd, but that's just sort of the standard convention for solving problems like these. And as we get more complicated cash flow diagrams over the coming weeks, I think you'll see why we sometimes do that odd thing. But just to let you know what the standard approach is for future values versus annual amounts, that's what it is that the single future amount occurs in the terminal year of the annual series. Again, we use this standard bracketed notation for summarizing the problem statement. In this case, this is an F/A because we're finding F given A. This problem is an A/F because we want to find the unknown A given some known value F. So here's an illustration of a problem with future amounts and an annual series. Something something is going to save $10,000 per year. So that $10,000 per year, remember when you're saving money, that's as though you're having an income. That can be considered as an inflow. At an interest rate of 8% per year, how much will the savings amount to in 8 years? So, I'm sorry, in 7 years. This problem was worded a little bit poorly. It's not saying what's the total after 7 years, because to do that, you just add up the 10,000 times 7. What it's saying is, what's the future value in year 7 of each of those savings? All right, cash flow diagram will save her company $10,000 per year. You know, I kind of disagree with that cash flow diagram. I hadn't looked at it very closely before class, but remember, if it's saving her company money, then that should be considered as an upward arrow. So maybe I'll have to go in and change the notes. This happens to be a slide that was put together by the textbook manufacturer, not me. So anyways. The main point of what we're seeing here, though, is it's 10,000 is the annual amount, and then we want to find out what's the equivalent of that in 7 years. So what's the future value? So the approach here, 10,000 is the A. We want to find the factor for F/A. So go into the handout that I've given you, find the F/A. Here's the formula that we could use to calculate that factor for n equals 7, I equals 0.08. One of the common mistakes that students sometimes use is they'll put in the whole value for I instead of the decimal value. So if you put in the number 8 for I, you're going to get a crazy factor. You should use 0.08 for I. In each of these formulas, it's the decimal representation of the interest. All right, so for that 89,000 is the future equivalent of all of those amounts. So what it means is, what if instead of getting those savings each year, what if you just kept them in a bank somewhere? How much could you withdraw in the future? What would be the future equivalent value of those savings instead of taking them in each individual year? All right, one last thing to introduce. Now this is a new idea. We'd previously talked about P and F and A. This is the last of the abbreviations I'm going to introduce to you, and it's G. It's a gradient. The standard form of a gradient is it means that the amount is increasing by a constant value each year. So G, 2G, 3G, and so on. It's the sort of thing that it means, like, what if in year 0 nothing happened, but then in year 2 you had to pay $100. In year 3 you had to pay $200. In year 4 you have to pay $300. So the amount is consistently getting larger. And an example of a real-world situation when that maybe would come up is, what if your revenues are increasing? So it doesn't necessarily have to be an expense that's growing. It could be that your income is growing over time. So what we do in this kind of a problem where we have it increasing by a constant amount, the standard form is that in year 1 it's 0G, year 2 is 1G, and so on. And so actually year 0, year 0 is the present, and then in year 1 nothing happens. And this is like a point that is really tricky for students, because if you remember back to an annual series, the annual series starts happening in year 1, and year 0 is where it's kind of the annual series is moved back to when you're finding the present value. But here, you don't actually see the effect of the gradient until year 2. Beyond that, it's the same thing as the rest of the problems we've done. There are factors for these gradient type problems that you can look up or you can calculate based on the equations that I provided. If you know the amount of the G, you just multiply it by the factor, and then it will tell you the present value of that gradient. One last idea I want to refresh. Maybe it's been a while since you did linear interpolation. And I apologize, by the way. For those of you who've printed out the class notes, this is a new slide that I just put together yesterday, so it's not in the class notes. Okay, so linear interpolation. This is something you maybe did as long back as middle school or something, but let's say, for instance, that you know the value of 2 points, the x and the y coordinates of 2 points. And you want to find out what is the value in between those 2 points. This formula is what would allow you to find the y value for some x. So let's use real numbers, because that maybe will make it more clear how this formula is applied, linear interpolation. Let's say that you know there's 5 and 7 on the x value, and then on the y-axis 5 corresponds to 12, 7 corresponds to 18. And we want to know what is the y value when x equals 6, if that's our unknown. Now just by looking at it, you could probably, well, it's halfway between 5 and 7, and if it's a line, that means it's going to be halfway between 12 and 18. What's halfway between 12 and 18? Well, it's 15. And so, you know, by inspection, you can kind of get an idea of how it works. But if we want to substitute it into the full-fledged formula, it says here, first take your first y value, 12, and then you add how much extra y is there above that baseline y value. And how much extra y there is depends on the slope of the line and how far along the x-axis you've gone. That's basically what this formula is doing. Is it's saying what should be the y value when you're starting with some known value for y at the beginning of your linear interpolation. And I mention it to you because it is going to be on the back side of today's in-class exercise. Let's take a look at today's in-class exercise. All right. Here's the first problem. I'm going to be handing this out. What time have we got? All right, we've got 20 minutes. I think that'll be perfect. Here we go. There we go. To go get some extras. By the way, I think everyone has finished part one. As I was walking around, it seemed like everybody got that one real good. It's summarized as P/F. The amounts are slightly different just because of round off. Those factors are rounded off and your calculator isn't. And so in this case, the difference isn't so big, 29,175 versus 29,174.52. But sometimes the differences are much larger, especially when you have several steps and the error accumulates. All right, so here's the formula for the second problem. The second problem, doing the interpolation. Okay. Trying to use this is a little bit like signing your name on the credit card machines. It always looks ridiculous, right? I mean, my handwriting's bad, but it's not that bad. Okay, the solution I've got on screen I did a little bit differently than using that formula. I was just sort of doing it my own way here. 2.22145 is what you get by doing the interpolation. But if you actually solve for it by putting the interest rate into the equation, then you get 2.2197. And so on the homework assignment, you have a problem where they ask you to interpolate using the factor tables. And just be aware that when you interpolate, it's introducing error. And the reason for that is that it's not actually a linear relationship. The relationship, because of compound interest, is a little bit curved. So you'll see a difference between the linear amount and if it was actually calculated the full-fledged way. But you got practice with linear interpolation. Here's the last one. I first asked you to write the years on the cash flow diagram just to send home the message that the first G is seen in year 2. You don't see the actual evidence of the G in year 1. It's in year 2. And since it's increasing by 200 each year, then that's why we say G equals 200 for this solution. So this is a P/G problem. We're finding the present value of some gradient amount that keeps increasing. I equals 8%, N equals 4. So you can look that up off of the 8% table that's above, or you can do it the formula way. Excuse me? Why it's a higher value for, oh, the present value. Good question, really good. Why is it, why are the future values worth more? Are you asking why is it more than G? Okay, it's because the G is just the first one, but year 3 is 400, year 4 is 600, and so this formula takes into account not just the 200 every year. It's not an annual series. It's that the entire amount is kind of getting larger. So it's taking back to the present the 200, the 400, and the 600. It's taking the entire height of those 3 lines back to year 0. It's not just taking the 200 component of it. Great question. All right, well, we're out of time. So just as a reminder, I'm putting the grades into MU Online. So if you want to have a look at the grade book, I'd encourage you to do that. In my past experience, it looks better on an actual computer than rather on the mobile app that they have. The grade book's a little bit screwy. If you didn't already pick up your homework assignment that's being returned, it's on the table back there. And I will see you in class on Friday. Please remember to bring your laptop. It would be very helpful if you can have your laptop. It'll let you get some hands-on with Excel. See you Friday.